My name is Ian Williams, and I'm a student with Professor Ostertag, and I work with Jake Duncan on this project studying environmentally damaged bridge columns, specifically in this test due to corrosion, and we have tested them, or we're testing them under hybrid simulation. So just as a little background and motivation for what we're doing, this is kind of the state of bridges in the US right now. Of the 600,000 or more bridges in the US, and 67% of those are reinforced or pre-stressed concrete, and we're seeing that 9.1% are structurally deficient. And that's about over 100 billion in backlog repairs, according to ASCE. So a lot of deficient bridges in the US, a lot of need for repair. And then if we look at a map also of seismicity, we can see that over 30% of the deficient bridges are in high seismic areas, and 77.9 with moderate to high seismic hazards. And really, there's a lack of data on how these corroded bridges and deteriorated bridges will perform in under seismic events. And so that's kind of where this research comes from. And if we can look at some of these corroded bridges, corrosion is kind of the leading cause of this damage. And we see it due to the embedded steel in reinforced concrete bridges. According to the NECE, there's approximately 17 billion spent every year on corrosion-related repair. And then there's indirect costs due to repair, like traffic delays, etc. Looking at corrosion, just some background on the corrosion process. There is this initiation period that we experience. So in a pristine column, you have the cover, and it needs to initiate because when you pour concrete around steel, the high pH gives this passive film that actually protects the steel really well from corrosion. But when you have penetration of carbon dioxide and chlorides, you lose that passive film layer, and that allows this corrosion to begin happening. And so then we'll see a slow increase in damage before the concrete cracks, but once cracks open up, much more of the oxygen and chlorides and everything can come into the steel, and we see a lot more increase in damage. And then once the concrete spalls, then we're approaching that acceptable damage limit and kind of approaching the end of lifetime for that column. And so this is some examples of what this damage looks like. There can be complete spalling or splitting cracks. And as we see a lot of damage forming right at the plastic hinge region of these columns, which for seismic response is kind of the more influential region of the column. So a lot of the worst damage is in the most influential area. Looking towards testing, there are conventional methods of testing that we couldn't really pursue, like pure analytical modeling. There's a lot of models being developed, but I think they're not quite at the point we need for an accurate simulation of the entire bridge. And then especially with the corrosion bond behavior and cyclic scenarios, you lose a lot of accuracy. And then it's also difficult to test because for conventional testing, corrosion happens really slowly. You have this dormant period that you have to wait for initiation, and then the process takes several years generally. So large-scale testing can be difficult and expensive to do this in conventional ways. So we turn to hybrid simulation because this allows us to test smaller things, test a subsystem that's much easier to corrode. We can use accelerated corrosion to bring this 2-year, multi-year corrosion process down to 1 or 2 weeks. And then we are able to test smaller substructures, but get a full system response that is much more accurate. So the bridge that we selected is just a single column bridge. I think the model was originally a skewed model. We're only testing in 2 degrees of freedom, a lateral, transverse degree of freedom, and vertical. So we have removed the skew, so it's orthogonal to the abutments, and then our bridge spans are equal in length to remove the torsion effect, so that we can accurately test in 2 dimensions. So we take the purely analytical model and we've replaced the element towards the base of the column with our experimental substructure. So again, kind of that most influential section we've replaced with our experimental element, and we have different ones that are either non-corroded or corroded. Again, just going back to the model, we are kind of replacing the lower half of this column with our experimental element that's corrosion damaged. We're controlling 3 degrees of freedom, so we have a 3 actuator setup that allows us to control axial, lateral, and rotation about that top node. But we aren't applying torsion, as I said. Here are the experimental specimens. We did have to scale them quite far down based on just the size of our project and being able to corrode these specimens, because the specimens themselves need to be lifted in and out of saltwater baths and moved around quite a bit. So doing anything larger than roughly a 50 or 70 pound specimen just isn't very feasible. So we went down. I think our scale factor is about 8, so that is quite a big scale factor down from the model, from the prototype, but it's kind of really as large as we can go. And then we've added some salt, some chlorides directly to our concrete mixture, and that is to remove that initiation phase. So that phase that usually you have to wait for chlorides to penetrate, we've completely removed that to speed things up. So then we can go into our accelerated corrosion process, where we apply this over potential, and that applied potential drives this corrosion process. And we see within 1 to 2 weeks cracks forming that are very similar to what you would see in a naturally damaged column. And we're kind of going until we see cracks that are objectively similar in nature. So what we're looking specifically at is these long splitting cracks that form along the rebar. It's kind of difficult to see in this image on the left of our actual specimen, but there are quite a few cracks there that go along the rebar and a few transverse cracks. So we're looking at similar damage. For the test itself, we looked at a lot of ground motion selected using Jack Baker's method, and we selected 3 representative motions of a minimum, median, and a maximum level motion. So Chi-Chi, El Centro, and Northridge are the motions that we went with for our specific structure. Here is a look at our test setup. We were a little limited by what we have in the lab at Davis Hall, so a little of this is pieced together just based on what was lying around, but it seems to work pretty well in our initial tests. So we have our two actuators controlling axial and moment going vertical there, and then we have a 60 kip actuator for our transverse displacement. And then here is an image of the actual setup in Davis Hall. Just to give you a scale, the whole thing is about 6 feet tall. So pretty small setup. Back in March, we did some preliminary tests just to make sure the setup itself was working and the communication links were working, where we controlled only 1 degree of freedom. And that's this plot on the left. And the red is our hybrid simulation with 1 degree of freedom. And you can see that, especially compared to the analytical simulation, and this is the non-damaged, non-previously environmentally damaged column, we're missing kind of a lot of these longer modes with only controlling 1 DOF. We then updated it to control 3 DOFs, and we see a lot better agreement. We're capturing those long modes. But we're still kind of having some issues with the open fresco element. Originally, we were using the 3 actuator element, but it has some issues because it was designed for a 2D model, but our actual model is 3D since we're going in the transverse direction. So trying to update that to work with a 3D model has taken some time. And so until we do that, we didn't want to move on to our corroded specimens. So those are kind of sitting in the lab waiting to be tested, just awaiting. Well, now I think the 3D model is finished, so now we're just waiting for some other tests in the lab to finish up. But we're on the cusp of getting that. So I'm sorry I don't have more data to show right now. We were hoping to push it forward and get it done by today, but it didn't quite happen. So the current tasks, just making sure that OpenFresco 3D element is working. So we'll run some really small scale motions just to make sure everything looks right before we do the full test. And then we'll just go ahead and test those corroded specimens. And then in the future, we kind of want to do more. We want to see, okay, this is how these corroded specimens perform. Now let's see what we can do, how we can improve that behavior. And we're a materials group, so we look at the materials being used, specifically high FRC. This is our hybrid fiber reinforced concrete. It's gone through a lot of testing in our lab, both mechanical testing and corrosion testing. So this is a hybrid, meaning we use fiber hybridization. Michael, it's a little more than sprinkling in cheese, but I know the top one does kind of look like Parmesan, so I understand. But here, what makes this different, it says that with the fiber hybridization, you don't get this crack localization that you would normally see in an FRC. You get diffuse microcracking and a smooth transition as you deflection harden the material. And that gives it much better performance characteristics. So in some previous tests, we saw a lot of improvement. So in the left is a conventional beam column test that was tested by Vesna, and you can see that there was a lot of spalling, and just at 4% drift, this really looked like it was at the end of its life. And with the high FRC all the way up at 6% drift, really identical specimen more or less, you don't see spalling. You see the cover remains intact, much less damage, and much higher capacities remaining. As far as corrosion, there were several long-term corrosion. So these were natural corrosion instead of accelerated, where beams were pre-cracked and salt water was ponded and just allowed to naturally corrode over the course of several years. And the initial pre-cracking, you could see that given in conventional concrete, the normal crack pattern allowed that salt water to penetrate much more than in the high FRC. You don't get quite as large cracks, so you don't get as much penetration. And so let's see, conventional, this is just the surface characteristics. You you see a big crack, a lot of corrosion products on the conventional, and the high FRC, very, very little. The state of these beams afterward, the conventional had a large splitting crack. You can see that the rebar itself on the top, maybe it's a little hard to see, but there was a lot of material missing from that, whereas in the high FRC beam, it looked almost pristine. And then just here's some tests. Let's see, so the black curve is the original high FRC beam with no corrosion. Red is with corrosion, at least the same length of time given to it. And so you see very little decrease in performance of those. Whereas with the conventional concrete going from the black dotted down to the yellow, you see quite a loss in capacity. And this beam here that you see that large crack, we weren't even able to do a proper test on that because it was so cracked, it had no capacity left. So yeah, this shows that with the use of high FRC, we're able to extend that initiation period quite a bit, and then even during the propagation period, we can extend that. So we're extending the life of these structures a lot. So given that, we hope to then, maybe with this next round of RFPs, do repeat these tests. Since we have the setup, have all the form work, everything's ready to go. Should be pretty easy to repeat these tests with high FRC and see what kind of improvement we can get. So just to kind of circle back to our original experiment, we saw that hybrid simulation is really the only way that we can test these specimens and get this data on corroded bridge columns. And that hybrid simulation is a low-cost alternative, and we do get accurate behavior of the damaged section. And then it's a repeatable test. So like I said, going forward into this high FRC test should be rather straightforward. And then just some acknowledgement, I'd like to thank, obviously, Jake, my research partner, and a lot of staff at Davis Hall. Salim Gunai has helped us a lot, and Andreas Schellenberg with this new element we're developing. And we will make sure it's documented properly. That's all. Thank you. Yeah.
Have you guys also looked at using Zypex or a crystalline-based admixture in the mix design itself and using that as a comparison? You might get a lot of free admixture material from manufacturers, so we might want to promote their stuff.
Yeah, I think right now we're looking mostly just at the fibers, kind of trying to eliminate too many degrees of freedom in our test. So it's not something we've looked at yet, but yeah, you're right, it would be interesting in the future.
Obviously, the main point is try to reduce cracking to reduce the fluid.
Right. Yeah. Yeah, I think, but also along with that, eventually you might get some cracking, like say you go through some small level earthquakes, even with the high FRC. But with the fibers present, you're holding those closed. So even if you do get some cracks, you're not getting nearly as much damage as you would see otherwise. Yeah?
Yeah, by high FRC, how high is high, and what kinds of fibers are you actually using there?
Oh yeah, sorry, I didn't go into that too much. So hybridization, we use 3 types of fibers. We have a 5 millimeter PVA, so that's controls micro cracks. That's at a pretty low percentage of 0.2%. And we use a 30 millimeter and 60 millimeter hooked end fibers at 5%, 0.5% and 0.8% respectively. And those control the meso cracks and macro cracks as they increase. And then we're also, because we're using hybridization, 1.5% is relatively low as far as FRCs go. Usually to see such good deflection hardening performance, you'd have to go up to 2.5%. So this, for constructability, is much more reasonable.
When you say percent, are you talking volume?
By weight.
So I guess normal fiber addition for production of concrete never goes beyond a couple of pounds per yard. So I'm wondering what the pound per yard we're talking about.
It's certainly much higher than that because usually right now most fibers that people are adding are just polymer fibers, right? And that's more for chemical behavior and for like controlling shrinkage and things like that. These, since they're mechanical, it needs to obviously be much higher than that. So constructability is a concern that gets brought up a lot. I actually recently constructed some smaller scale columns for some other research where I had spacing of 1.5 inches. So these 60 millimeter fibers are over 2 inches, and with a little bit of vibration, it flowed through a 1.5 inch cage, no problem. So it adds some complexity and makes it a little bit more difficult to build, but in the end it works.
You can cut them in half and kind of show how you got that consolidation with the cell methods. That will also speak volumes for its constructability.
Yeah. Yeah. Anything else?
Any other questions?